Well, greetings, mathletes, and welcome back. Today we're going to be talking about the inverse of an exponential function, right? So we saw exponential functions last time, and we saw inverses in the last chapter. We're going to put those things together and see if we can find an inverse for an exponential function. Now, this is a function you may or may not have seen it before, but I'm not going to bother saying the name. I just want to deal with it as an inverse of an exponential first, and then we'll talk about what it's called later. Okay, so I want to remind you a couple of things about inverses. Hold. First of all, one of the things, if you have a function, right, f of x, f is a function that takes an x and it spits out a y value, right? So you put in an x and you get out a y. F inverse then is a function that takes that y value and turns it back into the x value. Okay, so that's the first thing I want you to remember. Okay, so basically if xy is a point on the function, right, then yx is a point in the inverse. So it's literally swapping the x and y values. And the other thing, and we're not going to get to this part right away, but the other thing I want you to remember is that when you compose inverses, what you always get is the same value back. And it doesn't matter which way you compose them. You should always get the same value back if you have a true inverse. So for example, if my function was x cubed, we know that a cube root undoes a cube. So f inverse of x should be the cube root of x. So let's just plug in a value. Let's just see how this works. So f of 2, let's see, if I plug in 2, I'm going to be cubing that. So it's basically saying 2 to the third is what? And that gives me 8, right? If I come back over here now, and I take f inverse of 8, what I should get back is my original value. And the cube root of 8 asks, notice you're asking the question in reverse. What times itself 3 times will give me 8? And so it's asking the question in reverse, and that would get me back to a 2. So again, the function took an x to a y, and the inverse took that y value back to x value. Okay, so I want to remember that first of all. Okay, now let's look at an exponential function. So I'm going to take an unconventional notation here. I'm going to, well, let's try this again with the pen. I'm going to call my function f. And I'm going to start with a base 2 because base 2 is real easy to compute. So we can do a lot of the arithmetic in our heads instead of having to write down a bunch of stuff. Okay. Now here's the unconventional thing. I want to actually use a subscript to indicate which exponential it is, because you could also be looking at f of x is equal to 3 to the x, or f of x equals 5 to the x, right? You can have all of these things. If I just use a subscript, I can tell exactly which exponential I have. And so that's just going to make things a little bit more convenient. As far as I know, no one else does this but me. And actually, the only time I do it is in this explanation. Okay, so let's look at, let's see, we already have our function here. Let's look at f of 2, f2 of 3, right? So that what that means is that it is 2 to the third power. Okay, that gives me an 8. All right, so 3's turn into 8's. If I have an inverse, that means 8's have to turn into 3's. So if I take the inverse and that means I have to get a 3. Now, what I want you to do here is I want you to notice the relationship between this and this. So you notice you have a base of 2 down here. The answer is the exponent. right? Because before what had happened is F2 took the input was an exponent and the output was a number. Well, F inverse of 2, that means the input is a number and the output is an exponent, right? So that means that whatever this number is down here, if I raise it to this power, I should get whatever is in here. So let's look at a couple of others. I'm not actually going to mess with these just yet. We're gonna keep with the function base 2. So let's say I have f of f2 inverse of, let's just try some other numbers. Let's say 16. Well, here's another way to look at this that may help. 16 is 2 to the 4th. If you can rewrite it with an exponent, that helps make it make sense a lot quicker, because I can ask myself, 2 to what power will give me 2 to the 4th? Well, it has to be the 4th power, right? Because we were asking 2 to what power gave me 16. Well, I know 2 to the 4th is 16. So that means the answer is 4. And then you can go through and you can start messing around with these things with different bases. So for example, if I have F3 or F inverse of F3 inverse, there we go, of let's say 9. What I'm asking myself is 3 to what power will give me 9? And I have to square 3 to get 9, so that means the answer is 2. So the answer to these inverses are always the exponent, right? There's some other interesting properties too. Like if I have this inverse and let's say I just plug in a 3, right? So I'm asking myself, 3 to what power is 3? And the answer is 1. And it turns out this always works, right? If I was using the inverse base 2 of 2, right? 2 to the first power gives me 2. If I was doing the inverse of base 5 of 5, what I end up with is that 5 to the first power gives me 5. And so whenever the base matches the argument, and what you put into a function is called the argument, if you haven't heard that terminology before. So whenever the base matches the argument, the answer is always 1. So we can actually generalize that a little bit. I'm going to get rid of this. If I have an inverse of an exponential with base b, and I plug in the same base, if I plug the base into that function, it's asking me b to what power gives me b, and the answer is 1. Likewise, there's another value that does this, that no matter what which one you plug it into, you get the same answer every single time. And that's when you plug 1 into one of these inverses, right? So if I have the F2 inverse of 1, right? So I just picked 2 so we can compute it. 2 to what power is 1? Well, 2 to the 0 power is 1. If I have inverse base 5 and I plug in a 1, well, 5 to what power gives me 1? Well, 5 to the 0 gives me 1, because anything to the 0 power is 1. So if I'm plugging 1s into these inverses, it doesn't matter what the bases are, I always get 0. Okay, now this gets kind of fascinating because we can start computing these things even when the answer is not an integer, right? We've been looking at this as we get these whole number answers, but they don't have to be. Let me write this other property down. So if I have the inverse base b of 1, no matter what the base is, it always comes out to 0. So those are two very interesting properties. The other thing that's kind of interesting is if I look at base b -1 of b to the x, right? We saw that with the 16 thing. B to what power is b to the x? Well, again, it's the exponent, right? So this is actually the inverse property. And likewise, because remember, inverses, you can compose them both directions. That means that b raised to the f inverse base b of x is also x. And that's a weird little property, right? But these are the ways that you undo things. In fact, these two little properties right here are what we're going to end up using to solve equations later on down the road, right? These inverse properties. Oops. Okay, so let's take a look at some of these other ones here. What if I have f inverse base 3 of something like 1/3? Well, if I don't know the answer right off the bat, right? Sometimes it's actually really nice just to rewrite these things. I'm just going to give some value here. I don't know what it is yet, but I know that 3 to this value is equal to 1/3. And we have to remember our properties of exponents, but if I want the 3 to be in the denominator, that would mean that a would have to be -1. So 3 to the -1 is equal to 1/3, which means that these two guys have to match. So a is equal to -1. So f inverse base 3 of 1/3 is equal to -1. We can also do that with other stuff, right? Let's say I wanted to do 1/9, right? Well, I know 1/9 is 3 to the -2. So that means 3 to the -2 equals 1/9. So the answer is -2. Now, I think this is real interesting. We've actually computed all these things so far without actually knowing what the function is, right? We haven't talked about it at all. We can actually take this one step further. Let me get rid of some of this here. Let's add a function to the list. What if I have f base e inverse of x, right? I could have that too. So that means my exponential that it's the inverse of is e to the x. And these oftentimes, these ones base e, most of the time they end up being calculator problems. But it's good to understand how these things work. So like if I have f inverse base e of e to the 4th, the answer I get is 4. So it undoes that exponent and just brings it out. It brings the exponent down, basically is what it does. If I have in the inverse base e of e to the square root of 5, well, the answer is just the square root of 5. Right? It just brings the exponent down. And like it does with all of these bases, right? If I have the inverse base 3 of 3 to the negative square root of 54, something ridiculous like that, the answer is the negative square root of 54. Right? So it brings exponents down, right? It cancels the base and brings the exponent down. Okay. Now, I think we've gone far enough here where I want to give a name to these things. Oh, I don't want to get rid of that yet. I want to leave that up there. And that. Okay. F inverse base b of x is what we call a logarithm. This is what, and basically what we're doing, we're just taking the f inverse out and putting the word log in here. Right? And so this right here, this piece, is f inverse base b. right, is log. Now, it's a big name, and I think a lot of students get intimidated by the name, but look at how much we just did without even knowing what it was. It's just a matter of manipulating exponents. So if I have something like log base 3 of 27, right, I'm asking myself 3 to what power gives me 27? And it's 3 to the third power. So the answer is 3. If I have log base 4 of 1/16, right, 1/16 is equal to 4 to the negative 2. So 4 to the negative 2 power gives me 1/16. Right? So we can compute individual values of these just by being able to understand where they come from. Now, the other one here, now this base E is a little different just because it shows up often enough. This particular log has its own name. Right? This log is called the natural log. You don't write the E as a base, it's understood. The L comes first. I think it's a Latin base or something. It's probably logarithm natural or something. Excuse me, when you write it like that. But nonetheless, when you see ln x, what that is log base E of x, right? And that's on your calculator too. Although we're not going to be using it too much today. This is mostly about how to work these things out by hand, right? By understanding the properties of exponents and all that kind of stuff. Keep in mind, some of these answers are things like the square root of 3. If you put that into a calculator, it's not going to give you the square root of 3. It's going to give you a decimal, but you need to know that it's the square root of 3. So it's best to do these by hand just so you can get a feel. Because later on, when we manipulate these and start playing with the properties, it's best to be familiar with the arithmetic already so that the properties make more sense. Okay, let's go ahead and clear this off and look at some more stuff. Okay, so here's what I want you to do. I'm gonna jot down a few logs, and I want to see if, well, I'm not going to be able to see, but you'll be able to see if you can evaluate them. So this is one of those ones. I'm going to jot down a few problems. I want you to pause it once I get them written down and see if you can work this out. So let's see if you can compute the following. Log base 2 of 1/8, log base 3 of the square root of 3, log base 5 of 1 over the square root of 5, the natural log of e to the 1/5 power, and e to the natural log of 1 plus x. Okay, so I put a whole bunch of stuff in there. All of it, we've actually covered all the things you need to do to be able to do to solve these, but now they're all mixed up and they're a little bit out of context, so it might take a little bit more work for you to pull those memories back up and re-understand the problem. But go ahead and pause here and then see what you can come up with, and then we'll look at them together. Okay, so let's go ahead and work these guys out here. So the first one is log base 2 of 1/8. And so we're asking ourselves 2 to what power will give us 1/8? Well, I know 2 to the third is 8, but since this is 1/8, that means it's a negative exponent. So this is the negative 3, right? Now over here, 3 to what power is 1/2? And again, this is where it really helps to understand your properties of exponents, that a fractional exponent will give you a root of some sort, and it turns out it's 3 to the 1/2 power that gives us root 3. Over here, I got a root again, so I know it's going to be a 1/2 power, but it's in a denominator, which makes it negative. So this is actually negative 1/2 over here. 5 to the negative 1/2 power is equal to 1 over root 5. Over here now, with the natural log of e to the 1/5, now this is using the inverse property. right? I'm actually composing a function with its inverse, and so I should get back whatever that exponent is. That should be what falls out of here, and it does. It's a 1/5, right? Because if it helps, you can write in a little base underneath the natural log just to remember that it's base e. And so e to the 1/5 equals e to the 1/5. Now over here, this is still using the inverse property, but it's reversing the two functions. So it's putting the natural log in the exponent spot, right? Well, the e and the natural log cancel out, just like they do over here on the left-hand side. So what I'm going to end up getting is 1 plus x, right? And this works for the regular bases also, right? If I have log base 5, if of anything, x plus 27, I'll just make something up. Ooh, make it x squared, we'll get crazy. And if that's 5 raised to that power, the log base 5 and the 5 cancel each other out to give me x squared plus 27, right? So it's just whatever this argument is keeps popping out. So whenever you have an exponential composed with a logarithm, if they have the same base, they cancel each other, and all you get back is whatever that exponent is. So that's kind of fun. Now, I do want to point out one more thing, and there is another log that shows up quite, well, for lack of a better term, it shows up commonly, and this is called the common log. And that's a log base 10. Right? And we don't write the base 10 when we use the common log. So you'll notice it probably on your calculator, there's a button that just says log. It'll either say log or log x, but it'll say log. And that's a log base 10. When it's not written, it's a base 10. The natural log is base e, and anything else, the base is written, right? So if it's not a base e or a base 10, you're going to see a base written in there. All right, so I just want to summarize what we just discovered. Oops, I hit the wrong button. Let's try this one more time. There we go. Okay, so first of all, if b to the x is equal to a, then log base b of a is equal to x, right? It's the exponent. That's actually the definition of a logarithm. Most of the time people start that way, but I like to pack this in a little bit later. We found that log base b of b to the x is just equal to x. We also found that b to the log base b of x is also equal to x. We found that log base b of b is equal to 1, and log base b of 1 is equal to 0 all the time. And so those are some pretty important properties, right? There's actually more properties that we're going to be getting to, but these are the big ones. And then if I have the natural log of x, this is equal to a log base e of x. And if I have just the log of x, the common log, that means it's log base 10 of x, right? So that's some of the other notation. These guys still follow these other rules, right? These rules are still obeyed. It's just the logs look a little bit different. So I think your book actually separates it out and acts like they have a different set of rules, but it's the exact same set of rules. And so your task basically is going to be to compute a bunch of logarithms and make sure you understand them before we really jump into them with both feet and start depending on them. So I think that wraps it up for today. And so until next time, keep your pencils and your wits sharp.